So we're going through the B2 reflection solutions. And starting with question 1, some of you say you struggle with this, with the percents and how to use that information, how to calculate the percentages. So let's go ahead and go through that right now. At a California college, 22% of students speak Spanish and 5% speak French. 24% of people speak Spanish or French. What is the probability that a student does not speak Spanish or French? So I'm going to start by creating a table. A table is a great way to break apart data when you have this and this or stuff. So currently, we're going to actually start knowing that the the grand total has to add up to 100%. And we say 22% speak Spanish. Now, you might be tempted to put it up here or here, right? Let me get my nice pointer with a laser. There we go. You might be tempted to put it there or there, but it's the total people speaking Spanish, so I'm going to put the total right there. Then that means I can actually figure out what percent of people don't speak Spanish by subtracting that from 100%. So I know this is 22% and this is 78%. Then they say 5% speak French, so I'll put 5% is the total speaking French. And then they say 24% speak, I can figure out this 95% here because 5% plus 95% have to add up to 100%. We know 24 people who speak Spanish or French, right? And that means the people who don't fall into that category are the people who do not speak Spanish and do not speak French. So I'm going to go 100 minus 24, and that gives me 76%. Then I can go backwards, right there. I can go backwards from this value. Oh, wait, I don't need to figure out the rest of the table. I just need the people that do not speak Spanish or French, right? And that's my answer, 76%. But I can continue filling out the table. So let's go ahead and do that because it's going to be helpful for future problems. I can figure out backwards, this is 2%. And I can figure out backwards that this is 3% because I know I have 2% here. It's supposed to total 5%. So that's 3%, which means this is 19%. So part 2, or question 2, how do you find the intersection of two sets if it is not given to you? For example, question 2 asks the probability of A or B, so you would have to subtract P of A and B. So let's look at the table that we have filled out. So what is the probability the student speaks both Spanish and French? Well, that is just, we need someone who speaks Spanish and we need someone who speaks French, and that's that 3% right there. And that's the intersection of these two, which is that answer, 3%. Question 3 and 4 were hard because I guess for number 3 and I didn't understand how to find the probability of A and B. Well, that's a nice way to do an and using an and. To solve number 4, question 6 was also a struggle. So a couple of you struggling with question 3, probably because you didn't have this table. And they said, what is the probability that a student chosen at random from the college speaks Spanish but not French? So I want to be in the Spanish column and no French. So that would be this 19% right here, which gives you that value right there. Another thing you can do is you can actually create a Venn diagram. So we have Spanish and we have French. And then outside of these two circles are people who don't speak Spanish or French. So let me show you how to fill it in. We know that 3% speak both, so I put that there. And then we know that 19% speak Spanish, but they don't speak French, so it goes in this section. And then this section will be people who speak French but no Spanish, and that's 2% from up here. And then the people who don't speak Spanish or French, that's the 76% out here. So you could use a Venn diagram or the table. If you look, all these numbers right here are on the inside of these tables, so it's not the marginal numbers. Remember, we gave you roughly the marginal numbers plus one of the square. Well, we gave you one each of the marginal numbers, and you were able to figure out the other. And we gave you one of the squares. So between all that, it's like a puzzle. You can figure it out. For question 4, are independent variables not the same as mutually exclusive ones? correct. So for independence, there's a very particular way to figure out if two events are independent. Now, mutually exclusive means, let's say we're drawing cards. And if you've ever played with poker cards, there are hearts, diamonds, clubs, and spades. So you can't draw a card that's both a club and a spade. So those two are mutually exclusive, right? But if I drew a card and I told you it wasn't a spade, that changes the probability of you guessing the right card. So if I draw a card and say, oh, is it a heart, a club, or a spade, or a diamond, you just have a 1 out of 4 shot, right? But if I draw a card and I say, oh, it's not a spade, then you have a 1 in 3 shot of guessing the correct card. So if you know mutually exclusive, then that sort of helps you figure out some other things. So here we're going to check if these two probabilities, these two events are independent. So if two events are independent, then the product, well, the probability of A and B, this value right here we can find just by multiplying these two. But we're going to check it. We're saying it's independent. My bad. We're saying it is independent. So that means I can find probability of A and B, right? So initially, to use this formula, I need to find 0.25 plus 0.34, but I need to figure out this number right here. Well, if they are independent, I can just go 0.25 times 0.34, which is 0.085. And so I'll substitute that back in and add these two, subtract that last one, and I get 0.505. So the correct answer here is C. It's 50.5%, also known as 0.505. Question 5. I struggled with question 5 because I cannot identify what the error the student made. I also thought all of the answer choices were true, but I don't know why they're not. I struggled with the probability problems, specifically 1 through 5, and also number 7. I didn't know how to solve them. I struggled a lot with the first 5 questions. So here's the 5th question. There are 5 outcomes to an experiment, and a student calculates the respective probabilities of the outcomes to be, and here they are. The proper conclusion is that. Now, if you add these all up, they probably do add up to 1, right? But I got a problem where I can already see it. Can you ever have a negative probability? No, you can never have a negative probability. So the student must have made an error in their calculation. On to question 6. Question 6 was also a struggle because I don't know why the probability is 6 out of 10 and not 5 out of 10. So let's look. You want to use simulation to estimate the probability of getting exactly 1 head and 1 tail in 2 tosses of fair coin. You assign the digits 0, 1, 2, 3, 4 to heads, and then 5, 6, 7, 8, 9 to tails. Using the following random digit to execute as many simulations as possible, what is your estimate of the probability? So we want 1 head and 1 tail. So I'm going to pair these up. There's nothing I have to ignore. I have 1 digit for the first coin, 1 digit for the second coin, and I'm just going to separate them into pairs. So the first one is a 1, so that's heads, and then this one is tails, right? And then these two are heads, so I'll just go ahead and fill them out. So you can see, there we go. There's all the ones that we have. How many of these have exactly 1 head and 1 tail? Well, you've got that one, and this one, and this one. You've got a 4th one, and a 5th one, and a 6th one. Okay, so there's 6 out of how many? 6 out of 10. Number 7. I really struggle with the question about coin tosses and how many heads there would be in 1996 more tosses because I didn't understand at first. You had to divide it in half and not 2,000. So let's go ahead and take a look at this question. A fair coin is tossed 4 times. Each time the coin lands heads up. If the coin is then tossed another 1,996 times, so there would be a total of 2,000 tosses. That's what the person was talking about. How many heads are most likely to appear after these first 4 heads? Well, the main thing is, since the coin is fair over many flips, the head should come up half the time. Now, you're probably going, okay, but I already used up 4 heads. But here's the thing. It's a half and half for the future. Whatever happened in the past, you've got to ignore. So we only care about the 1996 flips, not all 2000. So half of 1996 is 998, and we expect 998 heads. It doesn't matter that it flipped 4 heads in a row first. So the correct answer is B here. It's 998. Question 8, I had a hard time visualizing probabilities without a table to help. I also struggled with number 8. After finding out the answer, it made sense. I just don't know how to approach these kind of problems. So let's go ahead and take a look. A basketball player makes 160 out of 200 free throws. What would we estimate the probability the player makes his next free throw to be? So by the law of large numbers, as you have a lot of trials, then you can say, oh, this is probably a good estimate of the actual probability. So we have some data here to use. And notice it says estimate. It doesn't mean this is going to be the actual probability. So we're just going to take 160 out of 200 and divide by 0.8. And since this is a large amount, we expect this to be a good estimate of the probability the basketball player makes any given shot. So 0.80 is the correct answer. On to problems 9 through 10. The most popular colors for cars and light trucks change over time. Here's a relative frequency table that summarizes the data of colors of vehicles sold worldwide in a recent year. What percent of vehicles would fall in the other category? Now, they did say this is percents. So what I'm going to do, and so they have all the percents filled in but one. I know the probabilities have to add up to 100%. So let me add up all the numbers except for this one that I don't know what it is. It's 98%. Well, if they have to add up to 100%, then I take away the 98%. That leaves me with 2%. Would it be appropriate to make a pie chart of these data? Explain. Well, if we use 2% for that, which it should be, right? These are all mutually exclusive events. You can't have a car that's black and blue as like the whole main color. You're at the vehicle's either black or it's blue. It's not both, all right? At least for solid cars. We're pretending solid cars, no pinstriping, nothing like that. So the main car color. So these are mutually exclusive, and when they're mutually exclusive and they add up to 100%, you can do a pie chart. So the answer is A. Next one, number 11. According to the Internet Movie Database, Avatar is tops based on box office receipts worldwide as of January 2017. Wow. Is it that recent? Felt like older. All right. The following table displays data on several popular movies. Which of the following is not a true statement? So I'm going to go through. When they say not a true statement, be very careful. You want to make sure that you write true and false on everything because you're looking for the false one. All right, so the individuals are the people who saw the movies. Well, is an individual a dollar amount? I don't think so. Well, I mean, you can't do a dollar amount per individual. I guess you sort of could, but here, the way this data is presented, this is one record. This is another record. So this represents one individual, and this represents another individual. All right. So the individuals are not the people. And we would argue the individuals are actually the movies, right? Time is quantitative. Yes, these are numbers. Genre is categorical. Yes, these are not numbers. Rating is categorical. Yes, you can see these are PG-13. Oh, there's a PG. Frozen did very well. All right. So the only statement that's false is A, and that's our answer. Again, especially when doing paper tests, if you see one of these not trues, go ahead and mark every statement true or false until you narrow down the one that stands out. The parallel dot plots show the total family income of randomly chosen individuals from Indiana, 38 individuals in New Jersey, 44 individuals. Which of the following is a correct comparison of the distribution of total family incomes in these two samples? So both of these have obvious high outliers. So I'm gonna guess these are kind of obvious. These are, you can see your middle's way over here. It's possible they're not outliers, but I'd say they're kind of obvious, right? So I'm going to say that's true. The median income for Indiana is greater than the median income for New Jersey. So I would actually have to count out data points. 44, so that's 22. So I've got 10 here. And then 1, 2, 3, there's 16, 17, 18, 19, 20, 21, 22. So the median is 49. For Indiana, I only have to count to 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So the median here is higher than the median here. So I'm going to say this is false. All right. So wait, this one is higher. Hold on. Let me double check. 1, 2, 3, 4. And we're doing 19. 1, 2, 3, 4 plus 7 plus 11, 17, 19's right here, right around 14. Whatever that line is right before 50. So it's aligning with this peak. This one is 22, so we got 10. And then 1, 2, 16, 1, 2. Okay, looks like they're the same. They're both in the same spot. So this is false. All right. New Jersey's distribution has both the lowest family income and the highest family income. Well, it definitely has the highest, but Indiana's actually just a touch slower than New Jersey, so that's false. The distribution of incomes for the randomly selected individuals in New Jersey has less variability than those of Indiana. Variability is how much spread you have. So which one has more spread? New Jersey does, not Indiana. And this one says it has less. So that would also be false. The distribution of total family income for Indiana is roughly symmetric, while this is slightly skewed right. I'm going to say there's a little, first of all, we know our peaks are right here, right? And I would lean towards a skew right. This outlier is pulling up the average, and these outliers are pulling up the average. So I would say both of them are skewed right and mark that as false. So we were looking for which one is true, and that would be A. Okay, for our next set of problems, here are the weights in grams of 17 Snickers fun-size bars from a single bag. So what we're going to do is I'm going to show you how to, we have to make a proper stem plot. I'm going to show you how to do it on Staplet, but basically remember that if you're doing by hand, you can just list these out in order. So 17.1 would be 17 and a 1. So these are all looking good, right? Do we have more than one 17.1? Oh, we have 3 of them. So I need, it's not D, and so I could cross that one off, right? So it's either A, B, C, or E. So I would just go through, and you could go ahead and list them in order, and that would make it easier to figure out which stem plot. I'll go ahead and show you how to use Staplet and create the stem plot there. So I'm going to use Staplet to go ahead and create a stem plot. Now you could do this by hand, but we're just going to go ahead and show you what's going on. We have one quantitative variable, just one group of data. And the data is weight in grams of Snickers fun-size bars. And then we'll paste the data in here, begin analysis. And you can see that dot plot is the first one that comes up. Hey, by the way, if you ever forget what the different graphs look like, you can always say, oh, that's a histogram. There it is, right? But here we're looking for a stem plot, and there it is. You can see that we have 15. If you're looking at your solutions right now in the packet, you can see that this matches solution A. So remember, if doing by hand, list the values in ascending order and don't skip any stems. We can see based on the stem plot we generated on Staplet, it is choice A. 14, which of the following characteristics of data is not made easier to detect by using the stem plot as opposed to the data set? So here's the data set, and here's the stem plot. Well, I think it's a lot easier to spot the gap, right? You can see it right there. The shape is definitely easier on the stem plot. I have no idea right there. The median is probably easier to spot here too, because you can just, like, it's already in order, and you can just kind of divide it roughly in half. We're pretty sure the median's either here or here. Actually, I'm pretty sure the median's right about there. Possible high outlier, definitely easier to spot. I mean, could you spot it here? Sure you could, but you have to kind of go through and compare and make sure that's the highest value, where it's pretty obvious right there. Number of observations you have to count in both cases. So this is the one that is not made easier by using the stem plot. Remember, when they say not easier, you got to figure out and write down your answers so you can make sure you get the right one. Okay, and for our last problem, the advertised weight of a Snickers bar is 17 grams. What proportion of candy bars in the sample weigh less than advertised? Round your answer to 3 decimal places. So I've kept the stem plot here that we chose as our answer. And what we're going to do is we're going to count all the values less than 17, because that's the median we're trying to compare to. So we've got these here, 1, 2, 3, 4, 5, 6, 7. So 7 are less than 17. Coincidentally, this feels a little weird. If I total them all up, see, I've got 9, 10 here. I have 17 total data points. So don't confuse that 17 with that 17. So if you got confused, you're like, why am I dividing this 7 by that 7? No, you have to divide how many are less than 17 by the total number of data points, which happens to be 17. That's a little evil, don't you think? So I wrote it out to 4 decimal places, but when you round to 3, that would be C. So again, if you struggled with any of these problems, please leave your answer in the free response, which is, what did you struggle with? What did you learn?